Okay, today's speaker is Ozgur Bayindir from the University of Paris 13. So his title is Algebraic K-theory of topological Hochschild homology of FB. So you can go ahead whenever you like.
Thank you very much, Cihan. And thank you very much for having me at Bilkent University. It's really a pleasure, especially because I actually had my bachelor's degree from Bilkent University. So I'm happy that I'm giving a talk in Bilkent. Okay, so as you can see in the title, the main result of our work is a computation of the algebraic K-theory groups of topological Hochschild homology of FP. That's the main result, and there is also another result that comes out of this work that is of interest on its own, we believe, is a new identification of THH-FP, this important object in trace methods, as an E2 algebra. So that's also a result that is a classification result that is of interest on its own. It's also a result we needed in order to obtain these algebraic K-theory computations. So yeah, so those are the main results. I forgot to set my timer that I always set when I started. Okay, so those are the main results, but of course, before I'm going to get to the main results of our work, oh, I guess I forgot to say this is a joint work with Tasos Moulinos. So I'll start with a quick background on algebraic K-theory and a quick history. And I'll try to give a few applications of algebraic K-theory. This first part of the talk will be a little fast, a little vague, a little hand-wavy, because it's more for giving motivation for what's coming after, but not really technical things that one needs to know to follow the rest. So that will be a little of a quick introduction. And then I'm going to talk about these trace methods for algebraic K-theory, where I'll start being more precise and slower. And so this trace methods for algebraic K-theory is a program that was developed in order to provide computational tools for algebraic K-theory. And I'm going to talk about that. And in particular, I'm going to talk about this recent Nikolaus Scholze work that gave that really gave a new definition of things going on in trace methods for algebraic K-theory, such as topological cyclic homology. I'm going to talk about that in detail because these are what we use in order to prove our main results. And I'm going to talk about our main results, its applications, and I'll try to say a few things about what goes into the proof of our main results. Okay, so the first place algebraic K-theory appears is the definition of degree 0 K-theory groups by Grothendieck. So if you let R be a ring in the classical sense, and PR denotes the isomorphism classes of finitely generated projective R modules. So that's a monoid under direct sum. And Grothendieck's definition of K0 of a ring is a group completion of this monoid. So that's his definition. If you look at this for the case when R is a field, if you have a field, then while every projective, every module is free over K, and the isomorphism classes are determined by dimension, and direct sum gives you addition of dimension. So basically this is PK in this case is natural numbers, right? Where, for each projective K module, you look at the corresponding dimension. And then its group completion is integers. So that's the K0 of a field, it's just integers. Later 1950s, Whitehead and Boss give a definition of the first algebraic K-theory group of a ring. That's given to be a Booleanization of infinite general linear group of a ring. And the intuition behind this comes from Tasos topological K-theory, where K1 would be, you know, defined using vector bundles on the suspension of a space. And looking at the definition of that, the gluing of for the vector bundles, the gluings somehow give you abelianization, somehow like intuitively correspond to this abelianization of the general linear group. So that's where the intuition comes from for this one. And the big application for this one was what's called the S-cobordism theorem. If you have a closed manifold of dimension larger than or equal to 5, this theorem states that what's called the Whitehead group of the manifold, which is K1 of the group ring on pi1 of M, okay, quotiented out by a subgroup of units, contains a topological information. It's pretty interesting because this object that is defined in a completely algebraic manner contains obstructions to this topological phenomenon, and it contains obstructions to triviality of H cobordisms on M. So if an H cobordism is a cobordism where the inclusion of the manifold is a homotopy equivalence, triviality means a cobordism being homeomorphic to a cylinder, right? So the obstructions of an H cobordism being a cylinder or not ends up lying in these groups. And this was like the big application of K1. And then later Milner defines K2, and their application is actually to number theory. The first applications that come for K2 was number theory. And the obvious question to ask at that time was, what about the higher algebraic K-theory groups, right? Can we define higher algebraic K-theory groups that will be meaningful? For example, that would agree with the previous definitions of K0, K1, and K2 as you would want them to. And for example, also behave like a homology theory. For example, if you have an ideal of your ring R, people would want to have a long exact sequence of this form, right? You would have this relative K-theory of R with respect to I, and then you would want it to fit into a long exact sequence of this form. And actually first Milner defined a higher algebraic K-theory, and then later it's realized that it wasn't really going to work. For example, his definition was only for fields, and it was becoming clear that it wasn't going to be possible to generalize to general rings and so and so. Actually, Milner's definition somehow didn't provide what is wanted, but what is still accepted today as the correct definition of higher algebraic K-theory is Coulin's definition. For a ring, Coulin defines algebraic K-theory in this way. These are the homotopy groups of a space. It again involves general linear group. And you take the classifying space and then apply what's called the plus construction. This is, again, this plus construction is by Coulin. He defines what this plus construction is for the purpose of defining K-theory. The plus construction does something interesting. It kills a maximum perfect subgroup of pi1 while keeping homology the same. So it's an interesting construction. So Coulin gives this definition. He doesn't stop there. He also does very important algebraic K-theory computations. For instance, he computes the algebraic K-theory groups of finite fields. And the result I just give you here. Actually, and after this, Coulin basically wins the Fields Medal for this definition and for his computations. So I told you that, you know, the application of algebraic K-theory of K1, and actually it turns out that algebraic K-theory of a ring contains a lot of information about the ring. Algebraic K-theory connects to number theory. It connects to manifold topology that I'm going to explain a little more. So it connects, it gives you information about a lot of things from different fields of mathematics. But the problem is that the algebraic K-theory happens to be pretty hard to compute, especially if you just try to use this definition. For example, Coulomb also tried to compute the algebraic K-theory of this ring. It's a very innocent looking ring that you would think that it should be computable, but actually Coulomb failed to compute the algebraic K-theory in this case. And actually, this is still an open problem now. And as far as I know, a lot of other people tried this too, and so far it's failed. Now people know a few things about these groups, but not completely. Another thing about connection of algebraic K-theory with other things and on the difficulty of computing these algebraic K-theory groups is the fact that, for example, if you look at K-theory of integers, it is connected to what's known as Van de Waal conjecture. This is a conjecture in number theory. I'm not going to give the statement, but if you look at the statement of this conjecture, it really doesn't look like it has anything to do with algebraic topology. But it turns out that it's that conjecture that is actually heavily studied in number theory. Happens to be equivalent to this homotopy theoretical question. And this is still open too. So this is still a conjecture. And so we don't know all the algebraic K-theory groups of integers either. Okay, so I actually just gave you so far the definition of algebraic K-theory of a ring. There's what's called Walthausen S construction.
Can I ask you something before you move on?
Yes, sure.
About the previous slide and these last two things.
Yeah.
So essentially, you don't know the p to the k for all k, or some k's you already know, or some dimensions you already know.
In here?
What is the story? The first one, the k to the n z,
this
p
one?
to the k. Yeah. And they're related questions, right? I mean, z and z to the k will be related.
Well, I mean, I don't know how related they're. One maps into the, you mean this question and Van de Waal?
Yeah, also that.
Yeah, somehow related. So this one, Coulomb-Lichtenbaum conjecture, which gives you all the K-theory groups of integers, as far as I remember. It gives you all the K-theory of groups of integers except these guys. As far as I remember, if I don't remember it wrong. And those conjectures are proved, and that was actually by work of Wowarski. So it came out of work of Wowarski that these groups are proved for except degree 4n. And these are not known completely for any k. But as far as I know, for k equals 2, there are some results, but I don't remember much of like exactly what is done at the moment.
Okay. Thanks.
Yeah, but
sounds
knowledge,
interesting though. Even the simple rings are.
yeah, that's why algebraic K-theory, I guess, is considered interesting. Simple things we don't know, and they're connected to important things.
Thanks.
So I was saying that I told you about the definition of algebraic K-theory of a ring, and even coming up with definition was somehow a big deal. And then there's the to define algebraic K-theory in a more general case, what is often used is the Walthausen S construction, which allows you to define algebraic K-theory of what's called Walthausen categories. And for example, the Walthausen categories are categories with a notion of cofibrations and weak equivalences. For example, if you start with a pointed model category, and then you just focus on the cofibrant objects, you get a Walthausen category. So this allows you to define algebraic K-theory in many settings, in particular of any pointed model category, algebraic K-theory of topological spaces, ring spectra, etc. I'll say a little bit more about ring spectra, give the definition a little later. So I want to fix a notation in here. For X, a ring, topological space, or a ring spectrum, when we say Kx, we mean the topological algebraic K-theory spectrum. That's often how people talk about algebraic K-theory these days, I think. Yeah, when we say Kx, we talk about the spectrum whose homotopy groups are the algebraic K-theory groups. Okay, so that's what I mean when I say Kx. And this was the application of Walthausen's algebraic K-theory definition for topological spaces. So Walthausen actually comes up with this S construction, which is very general, but the reason is that he just wanted to define algebraic K-theory for topological spaces. And if you look at his paper, he says, look, you may be blaming me for having such a abstract construction, but he says you will realize that there was no other way around. He almost like apologizes for being too abstract in general, but actually but of course, like his construction ends up being very useful because it was so abstract in general. And the big result that came out of one big theorem that came out of his work is the identification of the algebraic K-theory of closed differentiable manifolds. So he shows that algebraic K-theory of a closed differentiable manifold, the spectrum, the algebraic K-theory spectrum splits in this way. So this is the spectrum corresponding to what's called the infinite suspension spectrum. This is the spectrum corresponding to a topological space. It splits where this is the smooth Whitehead space of M, which is basically double D-looping of the stable pseudo isotopy classes of M. So that's some sort of a topological information coming from isotopy classes of M. So he shows that algebraic K-theory of spaces contain this information. Okay, so I said algebraic K-theory of ring spectra. And the rest of the talk I will be working in this setting because I told you, like, I mean, our main result is algebraic K-theory of THH-FP. THH-FP is a ring spectrum, right? And that's how we talk about its algebraic K-theory groups. Let me define what a ring spectrum is. The category of spectra is a symmetric monoidal category with the smash product being the monoidal, product. You need to be using a nice category of spectra, like symmetric spectra, EKMM spectra, whatever you like. It doesn't matter for the sake of this talk or work. So in spectra, a ring spectrum is defined in analogy by using this monoidal structure. You can think about the monoidal structure in analogy with the tensor product in abelian groups. So the correct analogy to have is thinking about the tensor product of abelian groups. And we say a spectrum is a ring spectrum if there is a map from X smash X to X that satisfies some associativity and unitality conditions. In other words, a ring spectrum is a monoid in the symmetric monoidal category of spectra. That's for example, you could define what a ring is, classical ring is, by saying that an abelian group R is a ring if there's a map from R tensor R to R that satisfies some associated unitality conditions. You just like replicate this in the setting of spectra. And this is a common theme in homotopy theory, actually. Whenever, I mean, yeah, it's a very typical theme. All these classical notions of algebra are often replicated in homotopy theory in the category of spectra by replacing basically all occurrences of tensor product with a smash product. And you can like talk about all these classical notion of ring spectra. You can define commutative ring spectra, algebras over a commutative ring spectra, module spectra, and so and so. Okay, and then an example. Let me give you an example of a ring spectrum. This will come up a lot. If you have a discrete ring R, by a discrete ring, I mean a ring in the classical sense. R, there is a spectrum called HR, the Algebraic spectrum. This is a unique spectrum that is given by the property that its degree 0 homotopy group is R, and the rest of its homotopy groups are just trivial. Okay, so this is like the Algebraic space, right? And it's uniquely determined, just like the way Algebraic spaces are uniquely determined. And this is a ring spectrum.
Sorry.
Yes.
So I have a question. Do you mean the homotopy category of spectra up there, or is just the?
No, the category of spectra. But of course, I'm assuming I'm working in a nice category of spectra, like symmetric spectra or EKM.
And for definition of the ring spectrum as well, it's just not in the homotopy category, but in the category of symmetric spectra.
Yes. Yes. Yes.
Okay. Okay, thank you.
Yeah, I mean, yes, there is some confusion because in the older literature, when people said spectra, they mean in the homotopy category, and some people may still be using that. So sometimes this causes confusion. But this is what is, you know, equivalent to A infinity spectra. This is at the level of the category of spectra.
Yeah, the reason I was asking the associativity and unital conditions, they're supposed to be up to homotopy, right? If you
no, no. When you say up to homotopy, then you are saying that it's a ring in the homotopy category of spectra.
That's what I was thinking. Yeah. Okay, but it's not.
Yeah. No, this is on the nose. Okay. It's also called A. I mean, this is equivalent to like A infinity algebras and spectra. So this is on the nose in the category of spectra. That's important. Yeah, so I was giving this example that HR, yeah, this is a ring spectrum. And the idea is that this is like, these objects are like having classical rings sitting in the category of spectra. At the level of homotopy category, this actually makes it a full subcategory of spectra. Makes classical rings a full subcategory of spectra. So yeah, for a homotopy theorist, or another way, for like a homotopy theorist who deal with this kind of stuff, a ring is just these HRs basically. So for example, if the K-theory of HR is same as the K-theory of that ring, okay. So that's the homotopy theory version of the ring. Okay, so I'm ready to talk about these trace methods. As I was saying, algebraic K-theory just turned out to be really difficult to compute, even very basic things. And to develop computational tools, I mean, it's not just difficult to compute, like people didn't even were able to develop basic like computational tools like spectral sequences, etc., by just looking at the Walthausen construction or the plus construction of Coulomb. But so in order to develop computational tools for algebraic K-theory, this program called trace methods came forward. I think it starts from 70s and late 70s, and it stretches all the way to today. it's a huge program, and the idea is to relate algebraic K-theory with other homology theories. So from now on, we're going to be working with...
Can I ask you a question before you move on to trace methods? So for spectrum or spectra, you can define algebraic K-theory in a similar way, or do you have to do something more than just what you do?
Yeah, you do the Walthausen S construction. Okay. The way it works is that take a ring spectrum, look at the modules over it. Okay. So in the module category, just take the compact objects and apply Walthausen construction. So it only the
But that is for differentiable manifolds, the one that you gave us. What is the Walthausen construction? Is to take the...
No, this is just a theorem. I actually didn't tell you how Walthausen S construction works. It's the whole complicated thing. Kind of basically, you get together maps in your category in a particular way with a certain combinatorics, and build a simplicial set out of it.
Okay.
And you loop it. The homotopy groups of that simplicial set is the Walthausen S construct, but it's a whole,
Okay, so this somehow includes the class construction and BGL inside it if you start with
they're equivalent, yes.
Okay, thanks.
They give you equivalent results. Yeah, I mean, I should have said that. Yeah, Walthausen generalizes the older one.
Okay, thanks.
Yeah.
Sorry.
Yes.
I have a quick follow-up to Ergin's question. So I remember this talk from Julie Bergner in Young Topologist. We were there together.
True.
So that can be applied to define, for example, K-theory on, say, a model category or something, because you define this augmented double category. Is that useful?
Yeah, this is like in general, you can define K-theory of like a general model category. And
so what you just said would be the same as constructing a nice double category that has properties so that we define the K-theory. I mean, never mind. I was just curious.
A double category and then do the, I see.
Because K-theory can be defined in any double category satisfying some conditions.
Yeah, I mean,
probably you would get that out of
I guess
nice model category. Yeah, it would be equivalent.
Things out.
Yeah, okay.
Okay.
Thank you.
Sure. Okay, so I was saying that, I was going to talk about trace methods. A spectrum is said to be connective if all its negative homotopy groups are trivial. Okay, so, and this is the setting that we will be in for the rest of my talk. And this is the setting where you can apply trace methods. So this, the big theorem in trace methods, I think the big theorem, but there are a lot of big theorems in trace methods. So if you have, it says that if you have a map of connective ring spectra where the map at the level of degree 0 homotopy is surjective with nilpotent kernel, if you're in this situation, then there is a pullback square that relates algebraic K-theory with topological cyclic homology. I haven't told you what topological cyclic homology is. I am going to do that. So algebraic K, but the idea is that TC is supposed to be more manageable than algebraic K-theory. And what is this saying? This is saying that if you have such a map from A to B, and if you know the algebraic K-theory of B, topological cyclic homology of B, if you know these two, then in order to get the algebraic K-theory of A, all you have to do is to compute the topological cyclic homology of A, right? I mean, you would also need to understand these maps and apply the pullback, but that kind of supposed to be easier. But really, the point is that it boils everything down to a topological cyclic homology computation. For example, this is often applied to the case where you map A to its degree 0 Postnikov section. So you're mapping A to this spectrum you obtain by killing all the homotopy groups above degree 0, right? Degree 0 Postnikov section. When you do that, then this is the algebraic K-theory of a ring, discrete ring, and TC of a discrete ring. Then computing algebraic K-theory of A becomes computing this topological cyclic homology. And this topological cyclic homology is defined using topological Hochschild homology. So this is, again, follows the theme I was telling you. Whenever there is a theory in classical algebra, you do it in spectra by replacing tensor products with smash products, and you transfer that theory to stable homotopy theory. And this is the idea behind topological Hochschild homology. So the idea, the definition of topological Hochschild homology is as follows: it's the realization of a simplicial spectrum. So when you have a simplicial spectrum, you can apply this geometric realization and obtain another spectrum. This simplicial spectrum in degree 0 is given by X, and then in degree 1, X smash X. It's basically at simplicial degree S, it's S plus 1 smash powers of X. And the face maps here are given as follows. The first face map multiplies these two X's. The second face map multiplies these two X's. And then the third face map does something funny, applies a cyclic permutation. It moves this X to the right, this X to the right, this X to the front, and then multiplies the first two X's after doing that. So, and you can just generalize to this to each step. And this gives you a simplicial spectrum. And THH becomes the realization of the simplicial spectrum. So THHX is another spectrum, right? And the homotopy groups of THHX are the topological Hochschild homology groups of the ring spectrum X. A big result in this direction is actually the definition is due to Böckstedt. This definition is very easy. I mean, it looks pretty simple today, only because we have a category of spectra with a smash product. When Böckstedt defined this, there was no category of known category of spectra with a nice smash product. So it was also a huge thing to be able to define this back then. So even that work, it was very complicated, actually. If you go back and look at that paper, it's a pretty complicated paper. It's not, but in today's setting, we can define THH in a very straightforward manner. And he does that. He defines topological Hochschild homology again for trace methods, and then he computes the THH of FP. And this is a highly non-trivial computation, but the result turns out to be very simple. So THH of FP is just a polynomial algebra with a single generator in degree 2, right? This is very surprising because when you think about this, you're doing smash products over sphere spectrum, right? I mean, whenever you smash two spectrum, you're smashing them over the sphere spectrum. So actually, the result here really depends on the stable homotopy groups of spheres. So it could be infinitely complicated, but you get this very simple result. So that's why this is such an important object. That's one reason why THH-FP is such an important object in trace methods. It comes from a pretty sophisticated place, but it gives you a very simple answer. Yes.
Excuse me. That cyclic definition, is that for all ring spectra or just commutative ones?
All ring spectra.
Okay. I mean, in the commutative world, this is tensoring with a circle, isn't it? But
yes.
But in the non-commutative world, that's not true.
That's not true, yes.
Right, but this is still a good definition of THH.
This is still the definition of THH.
Right, okay. Sorry, I always get confused about that point.
Yeah, sure.
Right.
Ozgur,
yes.
could you remind me how the Hochschild homology and cyclic homology were related here?
Yes, I will do that in a second.
Okay, thanks.
Yeah, I will first do THH and then TC.
Could you also quickly remind the maps in the simplicial object? What let's say the last two? You say there's a permutation going on, right?
Yeah, last two would be you multiply these two. That's one of the maps.
Okay.
You switch and then multiply.
Okay, and then similarly permutate the higher ones, and then.
Yeah.
Like
in here, you multiply these two. That's one map. Multiply these two. That's the other map. And then the last one applies a cyclic permutation and then multiplies first.
Okay.
Yeah, if you compare this result with the classical result of the Hochschild homology of FP, the older, classical definition of Hochschild homology, it gives you the same groups as abelian groups, but the ring structure is different. And it's interesting that you go to this is the divided power algebra over FP. It's interesting that you go to the category of spectra to a more complicated setting, but you get a simpler ring structure. So that's also an interesting outcome of this computation. Okay, so going towards the definition of TC. So there is this action of Cn at each degree in here, right? So C1 is the trivial group, so there is no action here. But C2, by switching the factors, acts on X smash X. C3 acts on X smash X smash X. And you end up having an action of Cn at each degree. Now, if you look at the simplicial circle and simplicial sets, in degree 0, it's C1, in degree 1, it's C2, in degree 2, it's C3. Because in degree 0, it's just the base point, in degree 1, it's the base point and the non-degenerate simplex, and it goes on like that. And you see that this turns into an S1 action on THH. So THH is always an S1 equivariant spectrum.
So here, do you think of S1 as delta 1 divided by the boundary? Like a quotient of...
Yes. Okay, so there's this structure on THH. There's even more structure that is exploited to define topological cyclic homology. If G is a finite group and we have a G spectrum, then there is what's called a norm map from homotopy orbits to homotopy fixed points. This is classically, if you were working with just G modules and taking classical, just straightforward fixed points and orbits, points at level. This map is given this way. For spectra, well, you need to do extra work to show that there is a norm map, but there is a norm map. And the Tate construction is defined, ATG, is defined to be the cofiber of this map. Okay, so you get this map, find the cofiber. And now we're ready to define what a cyclotomic spectrum is. But before that, I must tell you that cyclotomic spectrum and TC, these were defined in 1993 by Hsiang, Madsen, and Buxton. The older definition, though, was pretty complicated, and now it is being replaced due to this recent work of Thomas Nikolaus and Peter Scholze, where just 3 years ago, they gave a new definition of cyclotomic spectrum and topological cyclic homology, which is significantly simpler than the older ones. For example, the older definition made use of genuine equivariant homotopy theory, where the new definition completely avoids that and just uses naive equivariant homotopy theory. And of course, genuine equivariant homotopy theory is significantly harder than naive equivariant homotopy theory. And the definitions themselves just are simpler. If you would go back and look, I'm just going to give you the new definitions. But it's pretty surprising how much the older setting, it was possible to simplify the older setting. It's a really striking work. And so in this setting, a cyclotomic spectrum is an S1 spectrum with an S1 equivariant map from itself to its Tate construction. Now, the Tate construction has an S1 over CP action, but S1 over CP is also S1. So that's where this S1 action on the right-hand side comes from. So it's just an S1 spectrum with maps for each prime. That's where it is, at least since Nikolaus Scholze. And the big thing is that the reason we care about this in the first place is that THH of X is a cyclotomic spectrum, which allows us to define what it means, what topological cyclic homology means. So this is a theorem, but you can take this as the new definition of topological cyclic homology. That's how people think about it. So you define CX as the fiber of this map, right? Due to the theorem of Nikolaus Scholze. This only works for connective ring spectra, but it's not really a problem because we only do trace methods for connective ring spectra anyway, so not a biggie. So I defined what's in here. These are the homotopy orbits, sort of fixed points, and I defined what's in here too. You take a product over all primes. I defined what phi p is. That's what's called the Frobenius maps. But I just didn't tell you what can is. Can is, it stands for canonical. So you can factor the left-hand side, the middle term in here, as first taking the CP fixed points and then taking fixed points with respect to S1 over CP. Well, S1 over CP is also S1, right? So, and then THH HCP maps into THH TCP. And that's where this map can comes from. So if X is an HFP algebra, this is, so okay, like you looking at this fiber sequence, okay, it may look like a hell because you are taking a product over all primes, right? But the situation, this is a common thing in homotopy theory, you want to fix a prime and invert all the primes except that one prime, right? Like taking completion, or in case if you're working with an HFP algebra, then all the other primes are inverted. Then in that case, all factors in here except one of them dies, right? And your fiber sequence gets simplified in this way. So you just are left with one of the factors. And furthermore, this right-hand side happens to be equivalent to, in this situation, of course, it happens to be equivalent to the Tate construction with respect to the circle. And that has a name. That's called, that was already known. That's called the topological periodic homology. And this side is also had a name. This is called the topological negative cyclic homology. And so it's pretty nice, right? Like you have two homology theories that was already known, and TC is defined to be just the fiber of a map from the other. Okay, now I'm getting ready to give you our main result. From now on, K will denote a characteristic P perfect field. Perfect in characteristic P means that Frobenius of K is an isomorphism. Examples of this are FP is a perfect field of characteristic P. Finite fields are all such examples. Algebraic extensions of FP are, again, perfect fields of characteristic P. Bergstedt periodicity still works in this situation. Topological Hochschild homology of K is Kx2 as before. Okay, so we compute this relative K-theory in order to compute our K-theory groups. So what you do is that you look at this map coming from the Postnikov section map of THH of K to its degree 0 part, and then you take the fiber. That's the relative K-theory. The point is that due to the pullback square of Dundas with William McCarthy I showed you, this is the same as the fiber of this map. Right, so it boils down to a computation of topological cyclic homology. Now, the thing is that if, for example, K is a finite field, it's sufficient to compute this guy because this is due to Coulomb, right? We already know this for K, a finite field. And then you would, knowing this would give you the K-theory of THH of K. Okay, so we had this, and this is the statement of our main result. So we say, we show that the algebraic K-theory groups in even degrees are trivial. And in odd degrees, algebraic K-theory groups are given by what's called the big width vectors of length R in K. Now, these big width vectors on a commutative ring are the co-free lambda rings on that commutative ring. In other words, this is the right adjoint to the forgetful function. Length R means that you somehow like truncate these co-free objects. To be honest, we weren't expecting to get such a nice result. This is kind of surprising. Usually, if you look at the older computations of, or similar computations of algebraic K-theory groups, you often get results that are not this simple. It's usually the results look more complicated and a little bit more messy. So it is pretty surprising that we get such a simple result, and it would be really interesting to understand if there is a conceptual reason why we get such a simple result from this computation, because it just comes out of the computations in this way, but we have no meaningful reason why we get these nice objects as a result. Okay, a few applications of our result. Second K-theory of FP. So when you can compute K-theory of FP, that's a ring spectrum too. So you can compute the K-theory of that too.
Is it commute? I mean, what's the story about K-theory of a commutative ring spectrum? Is it a commutative ring spectrum, or is it just a ring spectrum?
Oh, it's also a commutative ring spectrum.
It is still commutative, right? Okay.
Yeah, yeah.
And I presume all those fiber sequences in the last few slides are all, when you work over a commutative ring spectrum, you're always going to get fibration sequences of ring spectra. Is that right? I mean, you wrote several sort of, right. So these definitions.
No, well, these maps.
I mean, these are maps of ring spectra, presumably. So TC is some kind of ideal?
I'm not completely sure about that part. I don't think this phi p is a map of rings. So if you, X is a commutative ring, this is a commutative ring, this is a commutative ring. But phi p, I'm guessing, is not a commutative ring.
What? Sorry, what was phi p? This is like the
Frobenius maps.
Frobenius maps.
Yeah, it seems like I switched notation for phi here, but that's the
yeah. Okay. Okay. I see.
Yeah, I kind of messed up the
ring map, right?
notation here, but
yeah. Okay.
So I think it's not a ring map.
Okay. Yeah.
I was going back one slide. If you can tell us, so K perfect field of characteristic P is necessary, and this doesn't apply to FP, I assume. And so, could you say a couple of words about bit vectors, how they show up, and comment on FP or things like that?
Yeah. So it's K. It works for K equals FP, right? K equals FP is an example of a perfect field.
Okay. So what's perfect field in characteristic P? Frobenius of
K is an isomorphism.
Okay.
The thing is that it makes it's Frobenius of K is an isomorphism, so it makes it étale over FP. That kind of like kills all these like homological extra information that may come over. So often in these situations, what works over FP also works for perfect fields. But you see in our title, we say THH of FP, so maybe that's like the base case we care about. Somehow these things often generalize to FP, but so the width vectors comes into play very often in these algebraic K-theory computations. And it comes into play in the spectral sequence computations. If K was FP, then width vectors on FP are the p-adic integers, for example. Okay, you get the P completion. And the width vectors does this over all primes, the big width vectors. So if you have FP, then width vectors of length R is just Z over P to the R. Okay, so that's a little bit. Well, why do these things come and show up? I don't know so much of philosophical reasons, but I know that it shows up in topological Hochschild homology, topological K-theory too. And there, I understand that the reason is somehow this: you look at vector bundles, and then there's this wedge product of vector bundles, which gives them lambda ring structures. And so width vectors are the free lambda rings. So that's kind of, there's that intuitive reason. How do these show up like precisely in the computations? Really, we just like compute the spectral sequences and you look at the extension problems and this just comes up, right? So our computation will not give you kind of a philosophical reason why these things.
So with this, you complete the calculation of KTH FP. Is that something that comes out of this or already known?
Yes, yes. You see, there's a fiber sequence, right?
And
so this works for K equals FP.
People didn't know KTH.
Yeah, this was not known, yes. So K equals FP. This will give you the relative theory between K-theory of THH FP and FP, right? So this gives you this guy, right? And then this is due to Coulomb. So we obtain this one.
That's nice. Thanks.
Thank you, thank you.
So I have a question. So the big
yes.
vectors, I think they also show up in algebraic K-theory of truncated polynomial algebras. That
of course, yes.
And relation, well, what's the relationship between? Or are they easier to compute than the computation that you did? Because like.
So actually,
kind of like
it's really like this. They are. So Martin's, it's Hessehold and Mattson where they compute algebraic K-theory of truncated polynomial algebras. Martin Spears, a student of Hessehold, recently computed that again, but using Nikolaus Scholze approach. And the combinatorics that work out in his work is very similar to the combinatorics of spectral sequences we have in here too. So it kind of like these width vectors show up in a very similar way. But in our case, we have like several theoretical inputs that we had to bring into the game, like that E2 identification I mentioned in the introduction. And so, the way these things come up in this from the spectral sequence computations is the same. It comes up for truncated polynomial algebra. So the analogy you made is accurate. It comes up in the same way, but again, like it comes up from these like spectral sequence computations, and we don't know a very good conceptual explanation for exactly why they come up. And I've been asking this to a few people and haven't got a good answer. Okay, so one application of this is the second algebraic K-theory of FP. I was saying this. This is an object of study that's somewhat interesting, and an object that was studied on its own. One reason is because this is not known completely, but there are things that are known about this. This is known to carry some information about homotopy groups of spheres, for example, the V2 periodic phenomena. So you can apply trace maps to TC and THH, and then apply the algebraic K-theory functor. So you can get the sequence of maps from K to KTC and KTHH, right? Because you can go from K to TC and then TC to THH. And we compute the right-hand side. We also identify topological cyclic homology of FP2. We show using an obstruction theory that this gadget is equivalent to co-chain complex on one circle. Okay, and then it follows from results of other people like Antio, Heller, Gepner, and Akil-Matu that this K-theory is same as the K-theory of the base ring in here of p-adic integers. So we identify that fiber sequence basically. We show that the midterm is given by this one, and we completely identify the right-hand side. And we argue that there are possible elements in here which may be detected through this map. So we kind of like show a scheme where one may possibly use for the computation of second algebraic K-theory.
Is KZP known?
Well, for P equals to yes, and for odd primes there is a description of this, but I don't know. I don't think people know the explicit description of the groups at each level, but there is a description of at the level of spectra due to Buck study, which I guess you can use to compute plenty of the groups, but I don't think it is completely 100% known. Another application is to what's called the fundamental theorem of algebraic K-theory. If R is a regular Noetherian ring, what's called the fundamental theorem of algebraic K-theory says that the K-theory of the polynomial algebra over R is same as K-theory of R. Regular, by the way, here means that global projective dimension is finite. So our results basically say that this result doesn't generalize to formal DGAs. What I mean is this: a DGA is a monoid in chain complexes under tensor product. Okay, so DGAs are basically chain complexes with an associative and unital multiplication. That's what they are. And DGAs generalize rings. If you take a ring, you can think about it as a DGA concentrated in degree 0, right? Or if you take and then you can do even more. If you take a graded ring, then you can think about this as a DGA, right? Degree I graded part would be thought of as the chain complex at degree I, for example. so if you take a graded ring, then you can also think about this as a DGA with trivial differentials. So DGA is basically, in a way, literally generalized rings. And formal DGAs basically give you these graded rings. Now you can ask if this question is, this equality is true for graded rings too, for formal DGAs too, right? DGAs with trivial differentials and have homology. So we show that it's not true for KX2. Like if you take this graded ring with polynomial generator in degree 2, because K is a field, it's Noetherian and regular. If the fundamental theorem was true for formal DGAs, the K-theory of this one would be equal to the K-theory of the base ring K, right? So, well, HC algebras in spectra, algebras over the Lambert-MacLane spectrum, is equivalent to the infinity category of DGAs. In particular, THH of K corresponds to the formal DGA with homology KX2, the formal DGA coming from this graded ring. And we show that basically our results basically computes the K-theory of THHK, but that's same as K-theory of X2, KX2. And we show that this is not equal to K-theory of K, right? So basically, fundamental theorem of algebraic K-theory doesn't generalize to formal DGAs. Okay, so I think this is a good point to stop, a natural place to stop.
Okay, Ozgur, thank you very much for the very interesting talk.
Thank you.
So
Thank you.
any questions for Ozgur?
I can have one question. How does this relate to earlier thing you said on the pullback diagram with KA, KB, and TCH?
Yeah, basically, yeah. In our case,
that kind of situation.
Yeah, I couldn't go that far in the talk. I was going to get into that, but the situation is that our A is THHK, and our B is small k. So what we do is that we compute the topological cyclic homology of THH of K, right? And then apply this pullback square. So RA is THHK, basically. Our B is just the degree 0 Postnikov section of THHK, which is HK.
So you use this to calculate K-theory of the THH?
Yes, yes. And this pullback, yeah, I just couldn't go that far in the talk.
But I was also asking, like, could you apply this to get to the K-theory of Z from FP? Or
yeah,
no?
I wish.
Because you already know some THH FP, and could you use that to, does it say anything about other questions that you were asking? Or?
Yeah, I wish it was, but those are all very difficult questions. We didn't think about it, but I think when you do this kind of stuff, you don't get to there. You don't get to those questions. When you do this kind of stuff, when you fix yourself to be over FP, and THHK is an FP algebra, right? In spectra.
Okay.
When you fix yourself to there, I think you're not going to be able to get out of that world. You won't be able to get out of the characteristic P world and say things about mixed characteristics. I think that's kind of the situation. But of course, it would be great to solve the Van de Waal conjecture.
Can I ask a question? In your abstract, you mention an E2 structure on THH of FP.
Yes, that's also another
Something
thing
about
I
that.
couldn't get to. Okay, so it's this theorem. So we show that THH of K is equivalent as an E2 ring to HK smash the infinite suspension of loops on S3. Now, S3 is an E1 ring.
No, right.
So its loop is
Yeah.
E2. S3 is E1 because quaternions, it's a topological group. So this thing is E2. We show that these are equivalent as E2. And that's an input. We believe it's an interesting result on its own. And it's an input to our computations too.
But of course, I mean, it is an it is already E infinity. So these two structures are not obviously related.
No, the right-hand side, like before smashing with K, no one even knows if this is E infinity or not, or at least no one I know.
Yeah, no, you're right. But I mean, the left-hand side, you have an E infinity structure.
Yeah.
So it's kind of weird.
It is pretty weird, yeah.
I mean,
it's not like immediately expected, but it is also known that these are equivalent as E1 rings, right?
Yeah, I'm just thinking about Dirichlet operations. I mean,
yeah,
you could plausibly see the difference.
yeah, you can see the difference. Yes, these are not equivalent. First of all, we don't know if this guy is E infinity in the first place.
Yeah.
And for example, you can see that THHK is not formal. We show that it is formal, basically. It's a formal DGA. It's a formal E2 DGA. And of course, THHK is not formal as an E infinity, right? Because it has Dirichlet operations.
Right. Right.
I have another question, but not completely related to it, this last part, but this K-theory of a manifold topological space you defined.
Right.
Does it have applications, or why is it defined? Or
what did I talk about it?
Huh?
Why did I talk about it?
Yeah, also.
Why is it defined in the first place by Walthausen? Yeah, I actually read that he had really questions from manifold topology of three manifolds in mind. He really had applications to manifold topology, but I don't know in detail exactly what those applications are.
Does he make any connection to the K-theory of rings from the K-theory of manifold? Is there a manifold whose K-theory is same as K-theory
Z? There is somehow, like, for example, to our work, there is a little bit of application. You see, this is the right-hand side here. If you take the K-theory of this, that's the K-theory of the three sphere, right? So K-theory of the three spheres maps into K-theory of what we calculate.
I see. Oh, yeah.
And actually, we are calculating at the moment the homology of K-theory of the three sphere, which is supposed to give us this pseudo isotope classes, whatever.
That's cool.
Yeah. Can I just ask? I mean, when you were talking about the manifold case, you have a definition of Walthausen K-theory, but if you look at the functional dual of a frame manifold, that's actually an E infinity ring spectrum. So you can form its K-theory. Are they related for frame manifolds? Are they the same construction?
Yeah, I don't know.
I mean, I guess the problem is you need some sort of orientability condition to dualize. So for frame manifolds, you essentially have that because they're self-dual. Well, stably self-dual. So my guess would be that the two K-theories should be the same in that case.
So can you say it again? Frame manifolds are self-dual?
Well, they're stably self-dual, right?
Okay.
So if you look at the functional dual object, so that's basically the map into the sphere. That's well known to be an infinity ring spectrum. So you could form K-theory.
Oh yeah, that.
And it's essentially that looks like it might be the same Walthausen K-theory, at least rough, at first guess.
Oh, wait, yeah, I guess it's often not. Because there's this result that says, for example, okay, I'm kind of guessing here, but there's this result that says, so what you do is kind of like taking cohomology and like K-theory of the cohomology. Somehow
Yes,
you're taking
yes.
cohomology with respect to the sphere spectrum.
Yeah.
There's this result that says that if you take the singular cohomology and then take the K-theory of that, you get the K-theory of the base ring. So it's kind of doesn't give you anything new.
Mm-hmm.
So I don't know what happens in the case of topological spaces. Like if you take the cohomology with respect to sphere spectrum and then take the K-theory of that, I don't know if that really gives you, I don't know. It's an interesting question, actually. There's definitely like something to think about.
Yeah, I don't really know much about Wallis and K-theory, so.
Yeah.
Yeah. Right.
Well, I have a question. So at some point you mentioned the V2 periodic phenomena. Can you say a bit more on that?
Yeah, it's
Like
just
your
known that, yeah, the second K-theory captures V2 periodic phenomena in spheres of the sphere spectrum. So
okay.
it does kind of like does the, it has height too in the chromatic sense. That is known, but not much else is known.
And how do you expect to capture information from your calculation? Because you calculated the target on the right and far right hand side.
Yeah, well, we don't have like a precise expectation, but we say that I'm just showing you a connection. So that there are elements here that are non-trivial, which could be captured in here, right? So this may be non-trivial, and then you can ask if this map captures those elements. So the non-trivial elements here, are they captured in here? And so and so. So that's kind of all I'm saying. It's just, you know, I just wanted to give a feeling of how things are connected. This is not like a program we're following at the moment, although unless we get a new idea or something.
Any other questions? Okay, then I guess it's time to thank Ozgur again. Thank you very much, Ozgur.
Thanks, Ozgur.
Thank you very much. Yeah, thanks for having me here. It was a pleasure, really.
Yeah, nice to have you here.